For years, Pluto's atmosphere held steady, behaving almost exactly the way scientists expected it to as the dwarf planet slowly drifted farther from the sun. Then, sometime around the middle of 2021, something shifted. Careful, repeated measurements started showing a real, measurable decline. And by the time researchers finished analyzing a full decade of data, they confirmed Pluto's thin atmosphere had dropped by 16% in just a few short years. Combine that with a series of strange, genuinely unexpected findings from the James Webb Space Telescope, and you get a distant little world that is behaving less predictably than anyone confidently assumed just a decade ago. We are talking about Pluto and a handful of recent discoveries that, taken together, paint a picture of a dwarf planet quietly doing things scientists did not fully anticipate. If your mental image of Pluto is still frozen somewhere around the 2015 New Horizons flyby, stick around, because the years since then have added several genuinely unsettling wrinkles to our understanding of this small, distant world, wrinkles that only became clear once researchers started comparing years of accumulated data against each other. Let's start with the atmosphere itself, because this is where the most recent, genuinely fresh unease comes from. Pluto follows an extremely long elliptical orbit around the Sun, one that takes 248 Earth years to complete a single lap. As it moves farther from the Sun during this journey, scientists have long predicted its thin, nitrogen-rich atmosphere should gradually cool and begin freezing directly onto the surface as frost, a process that would eventually cause the atmosphere itself to partially collapse. This prediction dates all the way back to 1996, decades before anyone had direct data confirming whether it would actually happen or not. For years after that prediction was first made, the data remained frustratingly ambiguous. Following the New Horizons flyby in July of 2015, which measured Pluto's surface pressure at roughly 10 microbars, an almost unimaginably thin amount compared to Earth's atmosphere, researchers continued, monitoring Pluto using a technique called stellar occultation, watching carefully as Pluto passed directly in front of distant background stars, then measuring exactly how the star's light bent and dimmed while passing through Pluto's thin atmospheric layer on its way to Earth. Through the following years, that pressure appeared to hold roughly steady, staying at a stable plateau that gave researchers little clear indication of which direction things were actually heading. Before we go further, if this kind of slow, carefully assembled scientific mystery genuinely interests you, go ahead and tap that like button right now. It really does help this video reach more people who appreciate watching real patient science unfold. Then, in a study published just weeks ago in the Planetary Science Journal, a research team led by Amanda Sikafous at the Planetary Science Institute finally settled the question using 10 separate stellar occultations observed between 2017 and 2023. Their careful reanalysis found that Pluto's atmospheric pressure genuinely did remain stable from the time of the New Horizons flyby through roughly 2021. Then, starting in mid-2021, the picture changed. Between that point and July of 2023, Pluto's overall atmospheric pressure dropped by 16%. The clearest, most direct confirmation yet that the long-predicted collapse scientists have been watching for since 1996 has genuinely begun. That decline carries real physical significance beyond simply being an interesting number. According to researchers studying this shift, it likely means a meaningful portion of Pluto's atmosphere is now actively freezing and settling onto the dwarf planet's surface as frost, a direct physical consequence of Pluto's steadily increasing distance from the Sun as it continues along its multi-century orbital path. Scientists have pointed out that this specific moment represents a particularly interesting point in Pluto's long-term climate cycle, watching in close to real time as a slow, predictable astronomical process finally becomes measurable after decades of uncertainty about exactly when it would actually occur. If you are new here and enjoy watching real scientific predictions finally get tested against real data after years, or even decades of uncertainty, now would be a great time to hit that subscribe button because there is a lot more of this waiting for you. This atmospheric story connects directly to a separate, equally strange discovery made using the James Webb Space Telescope over the past couple of years. Back in 2017, planetary scientist Shi Zhang at UC Santa Cruz proposed a genuinely bold idea, suggesting that Pluto's haze particles, rather than gases, were actively controlling the planet's atmospheric temperature, absorbing sunlight during the day and releasing it back into space at night. Zhang openly admitted the idea sounded crazy at the time, and many of his own colleagues expressed real skepticism. But he made a specific, testable prediction that if his theory held true, Pluto's haze should glow strongly in mid-infrared light, a signal no telescope at the time was sensitive enough to actually detect. That test finally became possible once James Webb launched in December of 2021, and when researchers finally pointed its instruments at Pluto in May of 2023, the results matched Zhang's decade-old prediction almost exactly. Zhang described the moment with genuine excitement, noting how uncommon it is in planetary science to have a hypothesis confirmed this quickly. Within just a handful of years of first proposing it, that confirmation revealed something. Researchers had not previously understood that Pluto's atmosphere runs on a mechanism unlike anything else observed anywhere in the solar system, one dominated by haze particles rather than the gas-driven processes that control temperature everywhere else scientists have studied. That same round of Webb observations turned up other details that added to the sense that Pluto was not behaving quite the way anyone expected. Researchers confirmed ongoing seasonal ice cycles reshaping different regions of Pluto's surface over time, evidence that Pluto's atmosphere is continuously leaking material that eventually lands on the surface of its unusually large companion moon Charon, and, perhaps strangest of all, an unidentified chemical. Signal at a specific wavelength that matched nothing in any existing reference database, later found independently on Titan, Saturn's largest moon, nearly 1 billion miles away. Researchers studying that particular signal have been refreshingly candid, stating plainly that they cannot currently say what the substance actually is. Taken individually, each of these findings represents a fascinating, well-documented piece of real science. Taken together, though, they paint a genuinely unsettling picture of a world behaving with more unpredictability than its reputation as a frozen, static rock would ever suggest. An atmosphere that held steady for years before suddenly beginning to visibly collapse. A haze layer functioning as an entirely unique kind of planetary thermostat, confirmed only after nearly a decade of scientific doubt. An unidentified chemical compound connecting Pluto to a completely different moon orbiting an entirely different planet. None of this points toward anything supernatural or inexplicable, but it does suggest that Pluto's true behavior continues to diverge, in small but genuinely meaningful ways, from what researchers confidently expected going into each new round of observation. That divergence matters because Pluto remains one of the most difficult places in the solar system to study directly. No spacecraft has visited it since New Horizons completed its historic flyby back in 2015, and no return mission currently has confirmed funding. Nearly everything scientists have learned about Pluto since that flyby has come either from painstaking indirect stellar occultation measurements taken from telescopes here on Earth, or from a space telescope studying the dwarf planet from nearly 1 million miles away, rather than up close. Given those limitations, every genuinely surprising result carries extra weight, since researchers have comparatively few independent ways to double-check findings against a fresh, direct observation of the planet itself. It also helps to understand exactly why stellar occultations remain such a valuable, if unusual, technique for studying a world as difficult to observe as Pluto. Because Pluto sits roughly 3.3 billion miles from Earth, appearing as little more than a faint pinprick of light even through the largest telescopes currently available, directly imaging fine atmospheric detail from Earth remains essentially impossible using conventional observation methods. Stellar occultations get around that limitation through a clever geometric trick, waiting for the rare, precisely timed moment when Pluto happens to pass directly in front of a distant background star, as seen from Earth. As that star's light passes through Pluto's thin atmosphere on its way toward our telescopes, the gases and haze particles present in that atmosphere bend and scatter the starlight in specific, then blocking it out sharply, since Pluto itself has no sharp, hard edge the way a solid, atmosphere-free object would, by carefully analyzing exactly how that starlight dims and brightens during the brief window of an occultation. Researchers can reconstruct detailed information about Pluto's atmospheric pressure, temperature, and haze structure, achieving a level of precision, down to just a few kilometers, that no direct Earth-based imaging method could ever hope to match. This technique has been used to study Pluto's atmosphere as far back as 1988, giving researchers an unusually long, continuous dataset spanning decades, well before any spacecraft had ever visited the dwarf planet directly. That long observational history is exactly why the recent confirmation of a genuine 16% pressure drop carries so much scientific weight, representing the culmination of nearly 4 decades of patient, repeated measurement, rather than a single, isolated data point that could easily be dismissed as measurement noise or coincidence. It is also worth appreciating just how precisely timed this recent finding turns out to be, arriving at almost exactly the same time as several of Webb's most significant Pluto-related discoveries. Between 2023 and 2025, Webb confirmed Zhang's haze thermostat. Theory revealed ongoing seasonal ice cycles, documented atmospheric material transferring from Pluto onto Charon, and identified an unexplained chemical signal connecting Pluto to Titan. Then, in the summer of 2026, ground-based occultation data confirmed the atmosphere had genuinely begun collapsing after years of stability. Taken as a connected sequence rather than isolated headlines, these findings represent one of the most concentrated bursts of genuinely new Pluto science since the New Horizons flyby itself, arriving entirely through remote observation, rather than requiring another multi-year spacecraft journey across billions of miles of space. It is worth remembering, too, just how recently our entire picture of Pluto shifted from vague speculation into genuine, detailed science. For most of the 20th century, since its discovery in 1930, Pluto existed as little more than a faint, poorly understood dot, its atmosphere entirely theoretical until stellar occultation studies began providing real data starting in 1988. Even after that, decades passed with only indirect ground-based measurements to work from, until New Horizons finally arrived in July of 2015 and gave scientists their first direct look at the world hiding behind those measurements. In the roughly 1 decade since that flyby, the pace of genuinely new discovery has, if anything, accelerated rather than slowed down, driven largely by patient ground-based monitoring, and a space telescope capable of studying Pluto's chemistry in ways no previous instrument ever could. That accelerating pace of discovery is exactly why so many researchers remain reluctant to declare Pluto fully understood, even after a successful flyby and years of dedicated remote study. Every time, scientists believe they have settled on a stable, complete picture of how this small, distant world behaves, a new piece of data arrives that quietly complicates the story further, whether that means a haze layer behaving unlike anything else in the solar system, an atmosphere that held steady for years before suddenly beginning to visibly decline, or a chemical signature that still, even now, does not have a confirmed explanation. There is also something worth sitting with about how these seemingly separate discoveries might actually be connected in ways researchers have not fully worked out yet. Pluto's haze plays a direct role in regulating its atmospheric temperature, and temperature plays a direct role in determining how quickly atmospheric gases freeze and settle onto the surface as the planet moves farther from the sun. It is entirely possible that the same haze-driven thermostat mechanism Zhang identified back in 2017 also plays some meaningful role in shaping exactly how, and how quickly, Pluto's atmosphere collapses as it continues its multi-century journey away from the sun. Untangling that relationship, determining exactly how haze physics and long-term atmospheric collapse interact with each other, represents exactly the kind of follow-up question researchers are likely to pursue using both continued Webb observations and ongoing ground-based occultation studies in the years ahead. That kind of layered, interconnected uncertainty is really what makes current Pluto research so genuinely compelling to follow. This is not a story about one single, isolated anomaly demanding an explanation. It is a story about multiple independent lines of evidence, gathered using completely different techniques on completely different timescales, all pointing toward the same broader conclusion that Pluto remains a far more dynamic, far less predictable world than its reputation as a frozen, distant, You are subscribed with notifications turned on because both Webb's ongoing observations and Earth-based occultation studies continue tracking this small, distant world closely. And there is a very good chance the next round of data reveals something else about Pluto that quietly does not match what anyone confidently predicted going in. Another small crack in the tidy, settled picture scientists thought they finally had of this strange little world at the edge of everything we know. A reminder that even the most thoroughly studied places in our solar system can still surprise us. One careful measurement, one patient decade of monitoring, and one unexpected result at a time, right up until the moment somebody finally notices something feels off and starts asking exactly why, refusing to let the mystery sit unresolved exactly the way good science is supposed to work, patiently, honestly, and always willing to be surprised by what the data actually shows.